Hey, welcome back, everyone. And before we begin, I had like a couple of announcements. So the first one is about the project rubric that we discussed last time, right? And so this is the breakup. I haven't decided on like how many points I'm allocating to the project as such, like overall, but like this is like if it makes 30% of the grade, this is the breakup for like how much this will like each component will be from your final grade, right? So that's what I have discussed here. One thing to remember is that like your solution approach, like your implementation and your like overall results together, they make up like around 15%. And that is something that you'll be like focusing more on. And like I'll be specifically looking at how well you have utilized the knowledge that you gained from the course, like from the lectures, and then applied them to like a real world problem. So that's what I'm looking at there. And obviously, because this question has come up before, so I'm not looking at you coming up with a novel solution to a problem, because obviously that's not the goal here. The goal is like how well you understood the problem and then you solved it. And maybe like even if your results were like up to somebody else solving the same problem, that's not what I'm testing you on here, right? It's more like what exactly was your approach to solving a particular problem. You had your own reasons, so kindly like be articulate enough to describe them either in your presentation or the report that you'll be submitting. And yeah, so that's what I would like to point out here. Okay, so that's the first announcement. The other one, and maybe I should wait for some time, people are still joining. So people who are just joining, I just wanted to point out that this is like your final project rubric. So please go through this. If you have questions, you can just like post here and I can answer them. So that's the first thing. The other thing is the discussion forum that we have like almost every week. And that is like the total of all the discussion forum points will be like 10% of your overall grade. Now the discussion forum that's coming up this week is slightly different in the sense that I'll give you some research papers to read, and you will be submitting like a write-up of like reading, picking up some of those and then like writing a summary of that. And so you'll not be posting it here on the discussion forum, but you'll be submitting it like a homework. So like it could be a PDF file or it could be a Word file, and you'll have like 2 weeks to do that. So of course, like I'll come up with more information about it, but the discussion forum for the next 2 weeks is going to be different in the sense that I'll point you to some research papers, you'll be reading them, and then you'll be writing a summary of that. Okay. So those are the two important announcements for today. Now let's begin with the actual, like, any questions about project or people who are online, you can hear me, right? Okay, thank you. Thank you. All right, so going back to the lecture, if you have any questions, just feel free to type in the chat window and I can answer there. All right, so today we are talking about radial basis function networks. And because we've been talking about unsupervised learning, and because we've been talking about last time we were looking at self-organizing maps, and there we were looking at the pattern of the data and like getting some information out of that. So that's why I just like decided to go over radial basis function networks, because these are also neural networks in some sense. But like the way we train them is different, and the way we use them is slightly different. The way we like, so these can be considered as like some kind of shallow networks, but very similar to neural networks. But the training could be like a little bit different from the way we like. It's not necessarily backpropagation for these models, right? So that's what we're looking at today: radial basis function networks. And we'll see that in a lot of problems in like if you have data that's not linearly separable, or if you have a problem like where you need interpolation. So those are the kind of problems where these are applied as opposed to your feed-forward neural networks. Okay, so that's why we are looking at this today. And then I'll just like quickly go over radial basis function networks, when to use them, and training, how to train a radial basis network. And then there is a paper that actually gives a lot of variations of like this training, but we will like restrict ourselves to the most common way of like training these networks. But we'll also look at that paper that gives us like different variations of how to train these models. All right, so let us begin. What exactly is a radial basis function network? And I'm like, it performs both classification classification and a regression, but like a high level way of thinking about these is that you're again measuring some kind of similarity between like your input data and some like pre-existing vector or some like centroid type of a vector, right? So remember we talked about these similarity measures in other models where we had like, for example, in k-means clustering, we said that there is a centroid and then you're clubbing together these points based off of like how similar or how dissimilar these points are from the centroid. So it's pretty much the same thing, but slightly different in the sense that the overall structure, it is similar to a neural network, but a shallow network. Okay, so it's a shallow network. You have just two layers, and if we count the input layer, then three layers. But if you don't count the input layer, then just like two layers. So one is the hidden layer, and then the output layer. Okay. Now the hidden layer is a little bit different from the hidden layers that we've seen before. Of course, there is like some activation happening there. There is some input, but like the fundamental thing that we're looking there is similarity or dissimilarity. How similar or how dissimilar my input is to my hidden layer, right? So that's the fundamental idea. Let's begin with, okay. And like, as I said, like the hidden layer stores something that's known as a prototype. So it's a prototype vector, and we'll see what it is. Usually it is like some way of measuring Euclidean distance between the input and the prototype. So that's what the activation is. That you are like in some ways measuring the distance between your input and your prototype. And that prototype is your centroid. As I said, let's look at the architecture. And this is what it looks like. This is what this entire network looks like. And of course, you have like the inputs. So the x's here are my inputs, right? And then you have this hidden layer. I think this is like, if I can, a little smaller. Okay, so this is like my input, which is my training data, right? And these are my centers. And so this is my hidden layer. And then this is my output. So what exactly is like different or what exactly is new here? Because this looks pretty much like a shallow network, right? The different thing here is like if you're looking at the hidden layer, right? We are mentioning like some phi1, phi2, phi3, right? And those are termed as centers and not like what we had earlier, like summing them up and then a sigmoid and so on, right? So there is a slight difference here in the sense that you have some input, you're taking that, and then you're comparing that to a prototype vector that is a part of your center. So center is actually a vector that is measuring some kind of similarity between your input and that prototype vector. And then you also allow some bandwidth, which is your like, so think about this as like a mean and a standard deviation, right? So those prototype vectors have a mean and a standard deviation. And then you're trying to measure like how much different is your x1, for example, from that mu1 or mean one, right? And how much different is your x2 from that mu1 or mu2 or mu3, right? Okay, so all of that might not make a lot of sense. So let me just like quickly draw that picture here. Okay, so the exact thing we're trying to do here is that like these centers or these points are known as like these hidden layers have like these nodes. So the terminology is still the same, like these are nodes, but they have some characteristic instead of like being like just summing these inputs up and doing something. So they have these characteristics. For example, they have like mu1 and sigma1. So this is described by that. And most likely it's like the prototype is like a Gaussian kernel or a Gaussian function. And we'll see like how that works. So basically that's used for measuring the similarity between my x1 and that prototype vector. So this mu here is a prototype vector. And this is known as bandwidth. Okay, so similarly here you'll have like another prototype and bandwidth and so on, right? And so what exactly is happening? Because like these are used as nodes, so there's some kind of an activation is happening. And what is that activation? So that activation comes from the idea of similarity or dissimilarity between, like, as I said, between the input and these prototypes. And there are different like functions that can be used to capture that similarity. And one very common function that's used for that is the Gaussian distribution. So for example, like for this one, I can just write the equation and this will like clarify things better. So let's say for this like network, I'm using this function to find the similarity between X and my prototype, right? So because this is like a known, if I'm writing it correctly, and sigma is my bandwidth, exponential minus, and X minus square. This is a square up there, and so I is like this. I is like these nodes here, right? So now notice this part here, this up here. So I'm calculating the difference between my X and my mu's. That those are my like my points or my prototypes. And this is like this part is exponential, and so this is like my entire function using which I'm computing in some ways the distance between my input and my prototype. And then we have this like exponential that is kind of telling me high level that like if there is a high activation, if they're like really close to one another, then this output that I'm going to like get out of this node is going to be higher. And if they are like really far away, then that is going to be faint in some ways, right? It's going to go down if you look at this function, right? Because like the activation is going to be higher for the values that are really like clubbed together, they're close together. And that's like the exponential and the negative sign is something that's what that signifies. And also the sigma here is signifying the spread of the effect of that, right? If question? Sorry, louder. Yeah. No, I'm going to change that actually. So we don't use that exact. We don't use that exact. And so because of like a lot of reasons, this is like modified, and a modified version of this is used. So I'm just like showing you the original Gaussian function. Right? Yeah, so that's a valid question. It's a good question. And so because of like these reasons of like the way the data is, and the way like the input is, we don't use this exact function, but rather, and let me just like point that out here. So the phi of X is like in a simplified way, we have a beta that in some ways encompasses the spread, right? And then you'll have this exponent stays this, sorry, not like this. It's better to write it like this. Yeah, right. So we use some kind of a like, so we make these changes such that this beta in some sense encompasses the spread, and this mu in some sense takes the average, or like it is the prototype, right? And so experimentally, we have some values that we use for beta that we'll see just now. But I want to make sure that everybody is comfortable with the idea that we are like utilizing this function. And there are many different kernels that you can use. So this is like a kernel, right? So you can use other kernels as well to find the distance or the difference between X and mu. There is no restriction that you need to use this. But this is the most common one, right? So there is no restriction as such that you have to use this kernel. And we'll go into that. There is a paper that talks about like how different kernels behave when you're like using it with different data types. So that's there. But like, so yeah, I think that I covered that. So essentially what we've done is we have like replaced this part with this beta, and we have like some experimental values that we can use. And anyways, it's an input parameter, but like this is something that we have some idea of like what this beta should be to like determine the spread of my kernel. And then this mu, we will talk a lot about how to determine this mu. But for now, just think that this is some kind of like representation of your input, and then like a good representation of your input. And then for every input point, you're trying to figure out how much I'm deviating from that, right? So that's the high level idea. Of course, like we need to figure out how do we determine this beta and how do we determine this mu, because those are the essential parts of my nodes, and those are going to like determine my output, and then I'm going to utilize those weights in some ways to get what I need, right? So this is like the architecture, and let me quickly go over if I missed anything. So this part actually talks about what I just said. The computations in the hidden layer, which are these nodes, are based on a comparison with those prototype vectors, the mu's. And then every hidden unit will have a prototype vector. So this one, for example, mu1, mu2, mu3, and so on. And then this this neuron will compare the input vector to its prototype and will output a value usually between 0 and 1, which is a measure of your similarity. So for example, let me show you this one. Okay, for example, let's say I'm using like my digits data, right? And so I'm just like focusing on one of the nodes, not all of them. So let's say I'm like focusing only on one input, which is like my, let's say like 7, right? And so I have like all these nodes here. And these hidden nodes will have some prototype vector. And so that prototype vector usually is, has come from my training set, right? And so what's happening here is that let's say that like I have this as a prototype vector, I have this as a prototype vector, and maybe I also have a 1 and a 9 because they look pretty similar to my 7, right? And then here I will have some ways, for example, let's say I'm using this like Gaussian kernel, and I have like some ways of computing this x minus mu squared, right? So in some ways I'm determining the distance between this 7 and this 7, this 7 and this 7, and so on, right? And so this is going to output some score, right? This is going to output, let's say it outputs some weight 0.61, I don't know. This outputs some weight 0.41. This output weight 0.09 because this is like pretty far off from this. And this outputs a weight I don't know, 81, right? And so like, so we have like these, and we'll come to how we determine these prototype vectors. But for right now, just like imagine that I had these in some way, I had like some way of having them. So obviously, because we are measuring the similarity between my input and these prototypes, right? So my activation would be higher when they are like very similar. So for example, this one should be like very high. And I'm like, okay, so for example, this one has like 0.61. And then this one has like 0.41, and this is like really low. But this 9 here in some ways was like very similar to that 7, so that had some kind of a higher activation, right? And so we take like the highest of these. So what we do here is we are going to sum these up and take the ones that have like the highest activation for these. So like because we are summing them up, most likely we'll have like higher representation of 7. Right, so that's the fundamental idea. We're going to like talk about how do we use the weights and all of that, but that's the high level idea of what's going on in these layers. Okay, so then what happens in the output once we have like these weights determined, right? What happens in the output? Well, the output consists of a set of nodes, one per category, or it could be like just a single one, depending on like the problem that you're solving. But important thing to remember is that let's say you have like multiple categories, right? A classification decision is made by assigning the input to the category with the highest score. And so again, it depends like how the output layer is, but that's it. That's the architecture. We don't have like deeper networks, or we don't have like any further layers. That is all there is to my RBF network. And believe it or not, with a good choice of your kernel, with a good right choice of your function, and the right choice of your prototype and your sigmas, these are universal approximators, just like the neural network, like the deep networks, right? So these are considered, and it has been like proven in multiple papers that these are also universal approximators. So that's good news. But then the real issue comes in that like, how do we train them? Right, so all of this is good. This is the architecture, but how do we determine like these mu's and these sigmas, and then how do we get the output weights? And then that's the next question, right? Okay, so moving on. Okay, so this section talks about like the neuron activation that I just discussed, which is like that every neuron in the hidden layer will be a measure of similarity between an input and a prototype vector. And that prototype vector is usually taken from your input training set. Because remember the example with 7. So I had like those examples of 7 from my MNIST, right, from my data. And so I'm comparing the difference between my X and those inputs. And I'm getting some activation. Of course, like I have passed it through like a Gaussian kernel or a Gaussian function. But the important point is that we are in some ways looking at similarity between my input and my prototype. That's a fundamental idea. It's like very simple because like I am determined, like I have some predefined kernels, predefined prototypes. And then I also have a predefined like spread of like how far I can go in terms of like, because if you think about the Gaussian kernel and the spread, like the beta value, which is dependent on my sigma, right? So as I move away from the center, right, I'm actually like getting the activation to go to a lower value. So the farther you are from your like prototype, depending on the value of sigma that you chose, you're going to be farther away from the center and the activation is going to get lower. So that's the high level idea. And yes, so each neuron will produce its largest response when the input is equal to the prototype. Let's say like we found an exact match, so that's the highest activation. Okay. So coming to the training of these RBF networks. Now, there are many ways, and we'll see that there is a research paper that tells us that you can have like a complete supervised learning way of like training the RBF networks, or you can have like an unsupervised combined with supervised. But here I'm just like talking about the most common way of like training your RBF network, right? So usually high level training of RBF is done in an unsupervised way, but I would say that there is some element of supervised learning as well in the output layer, because like when we have to adjust the weights, that's where like my supervised learning comes into play. All right. So first, let's talk about how do we train the hidden layer. And even before that, let me see if I missed anything. Okay, that's fine. So the hidden layer, if you go back here, has several parameters. So the first issue, or like the first parameter that we need to figure out, is my prototype vectors. Because like we've been talking in the architecture about these prototype vectors and the difference between them and the input, but where do they come from, right? So first of all, we have to discuss that. And then the other thing is those sigmas or the spread or the variability that we talked about, right? So these are like two parameters, because like my Gaussian function is like parametric in the sense that it's described by like two parameters, my mean and my standard deviation. So it's very similar to that. Prototype is nothing but your mean, and your spread, your bandwidth, is nothing but your standard deviation in some ways, right? Because that beta actually depends on your standard deviation. So like experimentally, the first thing that we do is we set your sigma. And people have actually arrived at these results, like how to set that, because it's not like an easy way to obviously do. So I'll just like write down some of the known results, and this is what we do. So when we are setting like this sigma, like there are two ways. So the first one is that maybe I can come up with like this variable d max, which is the maximum distance between pairs of prototype centers. So let's say I have prototypes, and then I'm finding like the maximum distance between, like I calculate the difference between all pairs and get the max one, right? So that's one way of like, that's one parameter that I might need to set my sigma. Or I can have like an average of all the distances between the prototypes. Either one is fine. So if let's say I have this d max, right, then sigma, and this is a very well-known like experimentally tested result that this works really well, that if you've computed d max, then you just like compute d max over like square root of m, where m is the number of hidden nodes, right? So let me just write it down. M is the number of hidden nodes. And so like this is 1, 2, and so on, right? And okay, so that's one. The other way of like setting sigma, if you've calculated the average distance between all prototypes, right? Then the way to calculate that is like 2 times the average. So these again, like it's a very well-known result. And then just like a reminder that we are here interested in setting the value of beta, which was like nothing but 1 over 2 sigma squared, right? So so that's what you set for the sigma. And those are like two well-known ways of setting your sigma value. Okay, so here, like once we are done with like setting the sigma value, it has like a lot of implications. For example, like the complexity of your overall model. Like, so it depends on like how many nodes you have, right? And then it also is like dependent on the value of the prototypes and the value of the sigma. So you can have like multiple combinations. Like let's say I have like a lot of hidden nodes, and then the sigma values are small, right? And okay, let me also make you visualize what it means when the values are large or small. So for example, if we think about this beta parameter, which is like a function of your sigmas, right? So these curves get like, I don't know, narrower as like the value of beta becomes bigger, right? Because it's like inversely dependent on your standard deviation in some ways, right? So like if, for example, and I'm just like making this up, if this is like beta equals 1, then your beta equals 2 should lie like within this, like it becomes narrower as like the value of your beta is growing. So that's what I'm talking about when I say that these are like narrower. So for example, here with larger data sets, a small bandwidth, that means a smaller, a narrower value of beta, with large number of hidden nodes works well. Then with smaller data sets, it's the opposite, like because we want to avoid overfitting. So these are like some of the known techniques of like how to set this bandwidth. And then bandwidth should be set in a way that each point is influenced by a small number of prototype vectors, because so this goes back to the idea of like, remember in k-means clustering when we were setting up those centers or those centroids, right? So I really wanted the points that are close to my centroid to fall into that group and not like some points that are like really far away. So that's what this is pointing to. That's so again, like a lot of things need fine tuning here, right? But these are like some of the known ways of setting a good value for sigma. Okay. Again, we shouldn't be setting it too large or too small because like one might lead to underfitting or overfitting. So those are like some of the things that you need to be careful about when you're setting the value of sigma. Okay, so now coming to the actual prototype vectors. How do we get the prototype vectors? Because that's what determines the difference between your input and those centers, and then it assigns it to a particular center, right? So even before we go here, like think about k-means clustering. So in some ways, what we were doing in k-means clustering was that we came up like with these centers, right? And then we were allocating these points to those centers depending on the Euclidean distance between them, right? So here in some ways I'm doing like a similar thing. And also if you go back to the architecture and look at these nodes or these hidden nodes, these are those centroids in some ways, right? Because for every input x1 or x2 and so on, right? The input that's like nearest to my centroid will have the highest activation for that. So in some ways it will be allocated to that, right? And like one of the, like maybe I forgot to mention that. So one of the motivations for radial basis functions was this theorem, I think it's known as the Covers Theorem, or that actually talks about like if you have linearly inseparable data in a like a lower dimensional space, and if you just like project it to a higher dimensional space, then you can actually linearly separate it. Like you can separate it because it's like in a higher dimensional space with a linear separator. So that was the fundamental motivation behind radial basis functions, because usually these centers, right, they are in some ways representing those centers in a higher dimensional space, because many times they are like more than this like input size, right? And what we are doing is like we are taking that into a higher dimensional space where we can linearly like separate the data. That's the idea here. So yeah, of course, like that's a lot of information to process. We'll go into some like pictures and see what's going on, how we can like linearly separate it in a higher dimensional space. What am I talking? Because this is like completely opposite to what we've been saying until now. But this is something that motivated the idea of like Rbfs. Okay, so coming back to how do we get the prototype vectors, right? And one way is like just go and pick randomly any endpoints if you have, right? And just like make them prototype vectors. But then the issue with that kind of a technique is that like what happens if there is like an overrepresentation of a particular training point, right? So if there's like there are regions where you have like an overrepresentation or an underrepresentation, you're randomly sampling from that, then you might not get like good prototype vectors and you might not get a good result. So that's like one downside, but that's a possibility, right? One very common way of like getting the prototype vectors is this like k-means clustering algorithm. Well, why not? You have the training data, you can come up with those centers, those centroids, and those centroids can be the prototype vectors. And then all you're doing is you're checking the similarity between your input and your centroids, because that's effectively what you were doing earlier, right? So that's another thing. So that's like an important part of training. And usually we use k-means clustering when we are training the hidden layer. Okay. Sometimes there is a decision tree based approach. And one of the paper that we are looking at today talks about like using decision trees, partitioning the data into different sections, and then getting a representation of a particular like partition as a prototype vector. So then in that case, it might or might not exist, might or might not be a real point, but you just get a representation out of that split, essentially. And then the last one, again, which what like we will discuss a little bit, is the orthogonal least squares algorithm. And so this approach involves supervision, because the way we select the prototype vectors are like we keep training and we are looking at the prediction error. And you'll see that this is like a pretty inefficient algorithm. And so to make it efficient, we make sure that the prototypes that we are selecting are orthogonal. So now that should ring a bell when I'm talking about orthogonal, because if those vectors are orthogonal, then in some ways I'm trying to maintain some kind of like non-dependency amongst those vectors in some sense. And then I'm like making it a little bit more efficient instead of like picking up every training point and then making a prototype vector and then computing the error and then selecting or not selecting that, right? So that's what an orthogonal least squares algorithm does. Okay. And then comes the final part, like how do we train these? And these are like, believe it or not, pretty easy to get. In fact, you can get it through like a very well-known like pseudo-inverse algorithm, because like sometimes we have, and I'm going to write all the equations so that that'll make sense. It's just like solving a system of equations. That's what it is, like this part here, right? Usually. So let's look at like how do we train the final layer, and let me like write all the notations so that we don't, maybe just write it here. Okay, so let's say we have like these weights, one, depending on the number of nodes. So if like my number of nodes is m, so I'm going to have like m weights, right? And so this is what I need to determine. And then I have like this hidden layer. And remember, my hidden layer passed through that Gaussian kernel or that Gaussian function. And so I have like these hidden representations in some ways, right? So let me just like denote those hidden representations by an H. So I'm just like making things easier here. So let's say my hidden representations are H1, H2, and so on. And depending on the number of nodes, I'll have like HM hidden representations. And yeah, so this like each of these H's or HI, right, is like an m-dimensional vector, because like I have these depending on like the choice of my number of nodes, right? So that's my hidden representation. And let's say I have like observed targets as well for like every output, right? So let me just say that my observed targets are denoted by Y, like Y1, 2, and so on, depending on like however I have. Let's say I have N values. So then that's that, right? And so this is like we have to predict like prediction of N training points given by the elements of like this times this, right? Because if you remember the overall architecture, what I'm doing is I have to have the weights, right? Those are like the H weights. And then I have the output from my node, which is represented by my H, right? So if you think about your loss, right? Okay. What happened to my pen? Okay. Okay, this is strange. I'm sorry about this. Did I turn this off? Okay, yeah. Most likely I turn it off. It happened in yesterday's lecture as well in CS1, and we just... Okay, so as this is going to be H transpose, and H, as I said, is like the hidden representation. So let me just write it down. Okay, and my output target values squared, and then maybe I can add a regularizer term, may or may not, depends. Like let's add it, because that's the usual. So that's my loss for my final output layer. And the good thing is that I just have like one, and so I can just like solve this. So like one way of thinking about this is that I will just find the gradients. Okay. And if you just like rearrange the terms, find the gradients, I have like 3 to 4 lines, which I'm going to make shorter because you can definitely find us. I'll just like write the final result. So the final result that I get is this, right? So once I find the gradient, set it equal to 0, then I get the equation where I can get my weights, right? So if I set this equal to 0, and this, by the way, has like, this has all the partial derivatives like u1 and so on. So I'm like not expanding that, but that's like quite evident. And then like if I set this equal to 0, and then again rearrange everything, let me skip like 2 to 3 lines and quickly write the final equation. Okay, I think you've seen that in linear regression, very similar to that, right? So that's what we are looking at when we are trying to solve for my weights, remember? And then if, for example, this lambda is greater than 0, right? Then we need to have some way of, like, if lambda is greater than 0, then do we have like a way of solving for the weights? So yes, in some ways, if my matrix is like this entire thing is invertible, then yes, I can just like go ahead and solve for my weights, right? And so this comes from this is reduced to your linear regression problem, right? This is how the pseudo-inverse algorithm, where we can like get an analytical solution. And then of course, like if this is not invertible, you have ways to get like your pseudo-inverse and then solve for weights. So the point I'm trying to make here is that even for radial basis functions, to get the final set of weights is pretty easy. It's just like solving this equation, which is very similar to your linear regression, right? And then we definitely can have, as I said, a closed form solution if this is invertible, right? So basically, like, let me just write it. So we can just say my weights. Okay, so what happens here is that like in most of the cases, backpropagation is not required, because I can just like get an analytical solution using that, right? So backpropagation is not required. But then that's the case when you have a closed form solution, when this is invertible, when a lot of things hold, then yes, we don't need backpropagation. But in practice, we do need backpropagation because most of the times we don't have like a closed form solution. So we do some kind of an approximation of like this, just like we did in logistic regression, right? But like in theory, you can solve for like this weights without actually getting into backpropagation at all. So what is that pointing to actually? Like how is that like helpful? Well, if you remember in like multi-layered feed-forward networks, right? Backpropagation takes a lot of time. So these are pretty faster in terms of like training. And as I said, they are able to solve, like they are also universal approximators. So most likely they're able to solve most of the difficult problems. But of course, like in problems like computer vision, or in problems like when we need RNNs, when my network is like going deeper and learning certain rich patterns from that data, that's not possible with Rbfs, right? So I'm not like learning a rich pattern here. I'm just like solving for some kind of a pattern and some kind of a similarity type based problem. So don't think that like I can just use Rbfs for computer vision type problems, right? So that's that is there, but still like we have a way of like approximating or getting like similarity type output using these. Yeah, you have a question? Exactly, yeah. And in fact, I had a hard time like thinking whether I should be putting that like there in the syllabus or not. But I just thought, yeah, that's fine, because you will find RBFs in many, like even recent research papers, but they use it as like some kind of a data pre-processing type of a thing, to get like those patterns and then go from there and apply some other model. So that's why they're not as popular right now. But I still wanted to kind of introduce them because we will see them again when I talk a little bit about support vector machines. So you'll see like there is a very close relationship with support vector machines. So that's why I just wanted to introduce them anyways. Yeah. Okay, so going back to the training part, you can actually do like fully supervised learning as well. But then I would say, like personally speaking, I feel that that defeats the purpose of like using Rbfs. But then, yeah, you can train them. You can approximate, like, if we think about like fully supervised learning, what are we looking at first of all? Well, if I go back to my architecture, I'm looking at approximating my prototypes. I'm looking at approximating my sigma instead of like using them as some kind of input parameters from my unsupervised approach, right? So let me actually give you an idea of like what we are looking at when we are talking about like this like fully supervised type of an approach for this. So we just like simply make our life difficult when we are trying to use like fully supervised learning, because like, of course, my loss stays the same. I can like quickly write these equations to give you a high level idea. I is from 1 to n, and I weight minus pi I squared, right? And so basically I'm looking at computing these values, so sigma I, and I'm also looking at computing mu jk, which is like the kth element of the jth prototype, right? Because these are vectors, right? My mu's are my vectors. So I'll be computing all these values for a fully supervised approach, which of course I can. I'm not saying that we cannot, because like this will involve a more complex term. And then when you start updating it, we need to update all these parameters in addition to my weights. So that's what we're looking at. And that's why we don't want to do this, right? And one subtle thing here is that, like, although we're looking at the sigma I, so there are like 1, 2, 3, and so on. So like sigma for every different node. But in practice, we use like a constant sigma for the entire like training. So instead of like sigma I can use sigma to make it like simpler. But still, I need the derivative of all of these. And then I need to update these as well as the weights. So that's what like fully supervised approach would look like. So that's why we do the training part, like break it down into two parts. First part was the unsupervised, where I got my prototypes and my sigma. And then the second part was like just solving that analytical equation similar to linear regression. Okay. So having said that, let's look at this paper. For some reason, everything is behaving weird. All right, so this, like, even before we jump to the ways to train, when should we be using RBF networks then, right? So like the hidden layer of my RBF is created in an unsupervised manner. So in some ways it is more robust because I already have a good starting point, right? So in problems when like you have something like this, right? If I'm using like, for this data set, if I'm using like these linear separators, right? Usually it's difficult to get proper linear separation. And so then in problems like linear separability, I need to use Rbfs, right? Or like specifically because I remember doing this problem myself. So I don't remember which data set that was. And that's when I had to use Rbf. But I clearly remember like in a two-dimensional space, this data set looked something like this. Like, so let's say you had this, and then this, and then like you had like no way to linearly separate them, right? So the crosses and then these. So like you had these like small islands. And if you think about a decision boundary, like how do you come up with something? So basically you can come up with those nodes or your centroids that are going to have like a clean decision boundary as compared to like any other linear separator, right? So those are like some instances when you're not able to linearly separate your data. And if you think about it, what we are doing with those centroids is that we are taking it to a higher dimensional space, and then we have a linear separation there. And so it's easier to partition in these type of problems that you can find those islands there, right? So that's where when we use radial basis functions. And another thing that I wanted to point out was Yeah, this is an important point. So gradient descent is run separately for each output node. So let's say my output layer had like multiple nodes. So I need to run gradient descent for each one of them. So in some ways, like depending on your data set, that might be an issue. That might be a problem, and that might be like super inefficient. So those are like two of the things that you need to like weigh in, which is more important. Let's say the data was linearly, not linearly separable, and so you decided Rbfs, but then the data set size is huge. So like there's that trade-off that exists, right? So that's like depends. So depending on that. Okay, I think I already talked about this one, that feed-forward networks learn a more richer structure for certain problems like computer vision and like other text-related problems. And so we cannot use Rbfs there, obviously, right? So those are some of the things that you have to keep in mind when you're using Rbfs. Let's quickly go over this paper. This is a nice one because they talk about 3 different ways of training Rbfs. So, okay, for some reason it's taking forever. All right, so here I'll quickly go over what they're talking about. So the first one is one-phase learning. So only the weights are adjusted, and you're assuming that you have like the prototype vectors and you have the sigmas already defined from some like information about the problem or like some domain knowledge. So that's the first thing. The other is the two-phase learning, which we just talked about. Like ours is a two-phase learning because in my first phase, maybe using k-means clustering, I determined my prototypes and my sigma, and then I solved for my weights, right? So that's like two-phase learning. And this is interesting because this is like the main contribution of this paper. So after the initialization of the RBF network, utilizing the two-phased approach that we just talked about, right? So I came up with the prototypes, I came up with the weights, I solved for that, and here I am. Then I can pick that network up and then maybe fine tune the weights using different techniques that I know. Maybe run gradient descent a couple of times, maybe like make it a more deeper network, or maybe make it as an input to a deeper network and then determine the weights. So that's what, like, there are 3 different ways of doing that. And that's what this part is talking about. Like the architecture is adjusted through a further optimization procedure. So I would be a little careful here when I'm talking about this like 3-phase learning, and I would be careful in calling that a radial basis function network anymore, because you've attached more layers. And like theoretically speaking, that shallow network is your radial basis network. You cannot have like more layers to it, because then you're converting it to a deeper network. But regardless, I thought this is an important paper. And what they do is like they also show different ways of learning. One of them, one interesting approach is like this competitive learning. And because we have looked at competitive learning, so I wanted to emphasize this one here. The way they're doing competitive learning is that I have like these hidden nodes, and I'm like summing the H transpose W, right? And summing that up. But instead of summing them up, they're saying just find the winner of the nodes. And then just like keep doing that, right? So in some ways, I'm not like summing them up and taking the max or something, but I'm like just like getting the winner out of there. So that's again like they're tweaking the model in some ways and like utilizing different techniques to make it like give better results. And one like I would definitely recommend everybody to read is this like LVQ learning, in which they're using some ideas from the self-organizing maps that we talked about last time, and they are incorporating that into your radial basis functions. So different ways of training, but yeah. So a quick, I think there was one, might not have, but they've summarized it somewhere. Yeah, so they have summarized it like how they are like utilizing these different like classifiers. The first one is like 1NN, which is like feature vectors are classified through one nearest neighbor rule, the first hidden nodes, right? And then this is like the self-organizing map that I was talking about. And the third one is the decision tree. So I think we mentioned that, right? That we can get those prototype vectors using decision trees. So that's what they're doing here. Okay, so then there are results, and they get really good results with the, I think the LVQ. Okay, so the top ones are like one nearest neighbor approach. So getting the prototypes using the one nearest approach. So that's giving like, and this is the MNIST data set. This is the MNIST data set. And LVQ is the one that's using the self-organizing maps approach. So that's also giving a very high accuracy. And then the third one is the decision tree, right? So this is something like, this is worth a read. So if you have time, just like go and look at these different approaches of using radial basis functions. All right, so the final thing that I want to talk about is the orthogonal least squares algorithm. And this is the one that's most commonly used for like building this RBF network. And in fact, there's an improved version of this, like it builds on a very basic idea that how about I start with a single hidden node every time, right? And what I do is I try every training point, and then I come up with the best node depending on my prediction error. So what we do is we usually keep away like a holdout set, like a training set, and we keep comparing the performance of that like one node network. How is it predicting like my inputs, and then see, okay, this is a good like fit, and so let me select this. So this, like, if you think about this entire approach, it's like pretty inefficient because like for just like getting one prototype vector, I am running through my entire training set, and then I'm selecting one. And then I have like n minus 1 for the second node. Then I'm running through my entire n minus 1 values or my training data. And then I'm selecting the second node. And then I'm also doing the computation of the prediction and everything. So of course, this is a very inefficient way of like creating this network. But this is a known algorithm. And like it's okay if we are using it with a smaller data set. But this is not like the orthogonal least squares. With orthogonal least squares is like we try to solve this inefficiency. Let's just think about it. What exactly are we doing? Like in my sum r plus 1th iteration, I am having n minus r remaining points, and I'm adding 1 to my prototype, my list of prototypes. And also I'm also like calculating the error of my prediction every time. And based on that, I'm adding my prototypes, right? And I stop adding my prototypes when I see that the prediction error like has begun to grow instead of going down, right? So yeah, I mean, so that's actually pointing to overfitting because my error started to go up, and so like I have enough as like these prototype vectors, and so I should just stop. But then just think about the inefficiency that goes into it, because like just for one node, I'm running through the entire data, and then for the second node, I'm running through the entire data, and then this can take like forever, right? For bigger data. Yes. Yeah, so just like initially you just pick one, any training point, just random. And then the thing, that's a good question. So even for that one like selection of the first node, you're not just done with that random selection. You then compute your prediction error, and then maybe like this was below some threshold or something, so you don't select it, and then you reject it, and then you select the other one, and then you keep going, right? So believe it or not, this used to be like this like was used for a lot of problems, specifically like with smaller data sets. But like thankfully, we have a better way of getting the prototypes. And I would say like the most practical way is like go and do k-means clustering and get the centroids. That's the best way out. But this is also a known algorithm, so that's why I wanted to introduce that anyways. And so what it does is it takes this algorithm that I just talked about, like that takes one prototype and then tests the prediction error. But instead of just like taking this one, like any training point, we want to make it like a little bit more efficient. So we select a set of orthogonal vectors. Sometimes we even construct them, right, in the space that's like spanned by my hidden unit activations from the training data set. So it requires like few more steps, which I'm not going into a lot of detail here. But the whole point here is that those orthogonal vectors, like they make our algorithm more efficient because they restrict the selection of like all the data from my train, because you want to keep them like in some ways like restricted to that space. So that's like what it adds to your original algorithm. Yes. 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 Yeah, that's right. Yeah. So again, I don't remember using this ever. I don't remember using this, but because a lot of papers mention this, so that's why I thought I'll just like mention it regardless. But yeah, it's a pretty inefficient way of getting the prototypes. And in most of the like known problems, for example, for the MNIST, there are like very efficient ways of even doing like clustering and getting the prototypes. So I don't think we need these kind of algorithms. But yeah, just to like, it's good that it exists. right? It's good to know that it exists. Okay. The other thing is this fully supervised learning. I think I already talked about that. If we are doing a fully supervised approach, then we have to have the gradients of my prototype vector and my bandwidths. And then I have to update those in addition to my weights. So that can be done, but that's like very inefficient, right? And usually if you think about the loss surface of my Rbfs, it has local minima, and in this like entire training and updating the prototypes, it like usually your gradient descent might get stuck there. So for those two reasons, fully supervised is not used, but yeah, again, it exists there, right? Okay, so coming to the applications, the first one I think we discussed, linear separability. The other one is interpolation, and that's like a very interesting kind of an application of Rbfs. So what like interpolation is a special case of regression in which like every training point is a prototype, and so the number of weights is exactly equal to the number of training examples. And so you can solve that equation, right? This paper actually gives a nice overview, and this is I think somebody's thesis, but I really like this example. This actually sums up like how we can do interpolation really well. So they take a very like simple example, right? So you have like these radial basis functions like phi1, 2, and 3 for like 3 different points like x1, x2, x3, right? And just like one dimensional, very simple data, right? And what's going on here is that this plot, this blue plot is the interpolant graph. So this shows that if you have like these radial basis functions for 3 different data points, then to approximate the overall function, you can just like sum them up or put them together for every input point. And so you can get like a more smoother function utilizing these multiple functions for different data points. Let me quickly show you what this is talking about. So this is the equation that we solve, right? This lambda was our weights, right? This lambda was our weights. And let's say like the output is known, some function, and you can solve this equation, right? And if you can solve this equation, you can get these like lambdas, and using that those lambdas, you can get like these different functions for different points. And if you combine them, that's what your like radial basis function is essentially doing, right? So just like a good visualization of why we can use this as an interpolant, because like you can, for every point, you can like for every different fee, like every different, I don't know what to call it, function for every different point, you can just like use a combination of all those points to approximate some other function, and that is going to cover like your entire space, and then you can use it as like an interpolant, right? So, and even better than this, Wikipedia talks about this really better. So you can like quickly read through this. But radial basis functions, if you're using interpolation, if you have like gaps in your data and you're trying to interpolate somewhere, then radial basis functions are good approximators of that. That's another application of radial basis functions. And so like the point that I'm trying to make here is that like if you have this issue of linear separability, or if you have like the issue of interpolation, that's when these come in. And yeah, so that's that. And then finally, yeah, this paper, I think there was a computer vision problem that they are using this as a, okay, so this one just talks about like how we can train an Rbf and how we can estimate. So this is like mostly what we already discussed, except that they go into the details of like how to solve for this. So this is that's why I have that paper there. But this second one, I think, had an interesting application. Yeah, this one. So they're using this like radial basis network architecture that like is used to learn the correlation between like some facial pictures and their patterns, right? So they're actually combining this like radial basis functions with another network. So I'll just like jump to that part wherein they have done something interesting. Yeah. Yeah, so they are basically trying to like just by looking at a picture, can you determine the sentiment of that picture? So that's the problem that they're trying to solve. And so, for example, here like happiness, disgust. So every like they have a different network for each one of those. But the thing that I wanted to show you, that's here. Yeah, so there is a variation of this Rbf network in which they're doing something that's known as this connectionist normalized linear spline network. And so they've like updated your like radial basis function, or the function that the Gaussian kernel, with certain small like additions, in the sense that they're adding some kind of a, if I remember correctly, they were adding a linear term to the activation, and then the responses were like utilized for the output, and that was able to like really improve the overall performance of your radial basis function. So that's like page number 14 actually is the gist of like what we are trying to do. And so this is like, of course, a different type of a problem, a computer vision problem, then, but with a certain update to your radial basis function, they are able to achieve that. And I wouldn't say it's a small update because they do a lot at the end, towards the end. But this is like a nice application of radial basis functions. That's why I have that paper there. Like if you have time, please go and read that. And then finally, we have the implementation in Python. So this, I think they have a code for, I think we already discussed all that. This here shows like a linear combination of Gaussians to approximate any function, almost any function. And yeah, so we do have like, so this one actually gives you how, like beginning from k-means clustering, how you determine the centroids, and then using those, how can you like train your network. So this is like a good implementation. If you're interested, or if you're using it in your project in any way, you can just like jump to this one and like look at their code at least. All right, so that's all I have for RBF networks. I don't think I have anything else. Yeah, so I think that's it from my end. If you have questions, you can ask. Otherwise, that's it. Thank you.